speakers are Swing and Chumen, who will be presenting their talk when Asus IoT devices play hide and seek with security, a vulnerability adventure. Swing is a security researcher from Changting Tech who specializes in discovery and exploitation of vulnerabilities, including IoT and network security applications. Chumen is a security researcher focusing on embedded devices and has presented on multiple topics at HITB. Without further ado, let's welcome them on stage.
Okay, good afternoon, everyone. Today, we will take you on journey into the world of Asus IoT devices and their security vulnerabilities. And I'm Swing, and this is my friend Chumen. This presentation is divided into 4 parts: a background introduction, research on history vulnerabilities, and the discussion of some new vulnerabilities, and the final summary. First, let's talk about why pick Asus for our research. Asus is a big-name IoT device maker. They make all kinds of IoT devices, especially routers. But when it comes to security, their routers had some real problems in the past. Then, we will show our attack surface analysis of Asus router devices, and will look at some past security problems. This helps us understand what went wrong before. Finally, we will look close at a part called lighttpd, which is used the AI cloud service. This part is important and may cause security problems. And we found a few real vulnerabilities, and we will show how to change these vulnerabilities to run any code on the router. Asus routers are everywhere. They have got a big market and tons of different modules. So, if there is a security issue, it could impact a lot of people. To begin our research, the first thing we need is the firmware. Lucky, Asus makes this quite easy. We can download the unencrypted firmware directly from the official website. After getting the firmware, we use tools like Beamwork and the UBIF reader to open it and check what's inside. This gives us a solid base to continue our analysis. When doing attack surface analysis, we found that Asus routers often provide telnet and SSH. This lets user connect to the system for admin tasks or debugging. With this access, we can check which ports are open on the router. For example, HTTPD on port 80 or cfgserver on port 7788. These open ports are possible ways for attackers to get in, so they are important parts of the router's attack surface. And let's take a look at some key history vulnerabilities.
Okay, in 2021 at the Tianfu Cup, a vulnerability was found in cfgserver. This service is used to connect multiple ASUS routers. It uses a TLV format and packs a function by checking TLV type in the packet headers table. The vulnerability in the AES decrypt function, which is called by most functions. In AES decrypt, the size for malloc is created using CTX plus length. when length equal 0x FFA, or inter-overflow happens. It causes mallocs to request a very small amount of memory, leading to a heap overflow. Another critical vulnerability in this an HTTPD authentication bypass. In the HTTPD handle request code, the authcheck function is called to check the request. The authcheck function will check the request cookies contain ASUS token. It does three checks. First, it looks for the ASUS token in the request cookies. Then, it checks if that ASUS token is in the concert session list. And finally, it refills if the ASUS token matches any store service token, like IFTTT or ALEXA. Okay, in the function, when the token is new character and the user agent match the internal service UA pattern, if the NVRAM IFTTT token is not set, it will be null. When the NVRAM safeguard function is called, it will be return a new value. In this case, the user's authentication check will be bypassed. Okay, we have briefly reviewed some key vulnerabilities. Now let's show the second part. In this section, we will discuss vulnerability discovery and its impacts. After analyzing the HTTPD service and other services that are bound to the listening point by default, we turn our attention to identify additional attack services. In the process, the aicloud feature caught our attention. By adding aicloud, we will find that the relevant point service can be sacked. We checked the number of devices exposed to the international on our assert mapping platform and found it to be quite sizable. It means that if there are critical security vulnerabilities, the large number of users' security could be affected. As you can see, in addition to standard service, ASUS routers or display or lighttpd service exclusively for the aicloud feature, running on the point 4403. It represents a completely new and spread attack service. When analyzing the attack service of aicloud, we needed to focus on two key areas. First, the HTTP request processing mechanism of lighttpd. We know that the manufacturer often customized web server made to import Unicode features, and this customized processing logic may introduce security issues. Second, pay attention to the modules it loads. These modules provide expanded functionality for lighttpd, such as authentication or file access control. ASUS has also done intensive custom development on these modules. Experience shows that the components customed by manufacturer are often point to security vulnerabilities. Standard points are usually expensively tagged, while custom code may not understand those security alias, making them point to logic flaws or malicious errors. When analyze the aicloud service, we look at HTTPD standard command and configurations files. As shown in the feature, the configurations file is loaded multiple modules, which together from the functional foundation of the aicloud. One of the common features of lighttpd is this modular system, which we refer as modules. These modules provide lighttpd with extensible functionalities, including authentication, and so on. Since these modules directly implement aicloud functionality, we selected them for further attack services, focused especially on this handling user authentication and file request processing. We first studied the lighttpd processing mechanism of the lighttpd itself. In the process of studying the lighttpd handling mechanism, a serious buff overflow vulnerability was found. The file lies in the function and may be tracked when the processing the cookie handler in the request. This is a critical step overflow. And the length limit was added to the point buffer overflow. Next, we will shift our focus to lighttpd's module system. In the user authentication modules, there is also a critical step overflow vulnerability when process URLs. It pays also add a length limit. Okay, after analyzing several classical and simple memory vulnerabilities, let's turn to the logic vulnerability part with greater impact. The complete exploit chain we found, which enables read moment code execution before authentication. The main vulnerabilities identify are authentication bypass and command injection. Let's walk through the core logic. The several init throw on enables modules in the order defined by the configurations. For each module, it sequentially calls this function, and each call it checks the written value to decide whether to continue with the next module. There's two important written values to keep in mind. The handle go on, which has a return values of 1, means to continue and call the next module. Handle finished have a return value of 2, which means processing is complete and no further modules will be called. Next, let's take a closer look at the core authentication function of the aicloud module. Here's the key snippet and shortcode. As you can see, the main step are determine the authentication method, whether it's NTLM or BASIC. Initialize the SMB connection information. Call the appropriate authentication handler. Finally, decide to accept or reject the request based on the handler's written values. This function controls the combination or termination of request processed by written different. Here we can understand the general process of this function, and then we will each the relevant key functions for step-by-step analysis. Next, let's analyze how the authentication model is determined. The function follows the key logic. First, it retrieves the user's agent handler from the request. Then it goes through all the configuration context set in the server, and it extracts the special value. After that, it compares the user agent value against these values. Finally, if a match is found, it sets the connection map to NTLM. Then go back to the configuration information to view the key parts. Now, let's revisit the configuration to focus on the key issues. The issues occurs here. When implemented through configuration context, the function does not check if these configurations apply to the current request path. Instead, it directly expresses and uses specific values from the entire configuration. As a result, configurations that are means only for the SMB path ending up being wrongly applied to request for the root path. This is a critical configuration scope configuration issues. Next, let's look at this function, which initializes SMB connection info based on the request URL path. The main operator of this function include: first, press the URL path components, then determine the required type based on a value components. Next, setting the query flag to SMB host query for the root path when the server name is empty. Finally, configures the collection parameters according to the daemon query tab. This query tab flagging setting is normally for functionality in itself, but it has important implications for later authentication processing. Notably, this special handling of the root path actually become a critical link in the vulnerability chain. Look at the code. The main problems with this function are: first, it checks the query flag to decide how to authentication. Then it is in SMB query mode. It skips the actually authentication completely. After that, for any other cases, it goes through the normal NTLM authentication keys. Finally, the function returns handle assert, which has a value of 0. Pay attention to the key part of the function. When it sees the request is in SMB quest query mode, it jumps directly to the lamb 66, and this is the subsequent authentication check. It means that the request for the root path does not perform any authentication in ATLM mode, and then returns handcert to exit the function. Finally, let's look at how authentication results and handling in the function, which is the last case in the entire vulnerability. Here's the key part of the main handler function that deal with authentication result. First, it calls the appropriate authentication handler based on the connector mount. Then it checks the written value from the handler. After that, it only stops processing if the result is something else, then under assert. But if the result is handle assert, it only lets the request continue. It creates a security vulnerability where handle assert is only interpreted as successful authentication. It allows organized access. The right way is handle this is to check authentication as successful only when you get a clear handing go on response. Anything else, including handing assert, should be considered a failure. Okay, let's go back to our initial function analyze and walking through the full attack chain and the main points of this authentication bypass. The point 1, it applies a configuration from elevate context and ignore the path. Even though configuration is defined only for the SMB path, it's only applied to the root path. And the init function, it just normal handling for root path and is not a vulnerability by itself. The point 2, it completely skips the real authentication when the SMB query mode. This This happens because the code uses a goto statement to stop past the authentication step entirely. Thus, the point 3, it wrongly treats the handle assert response as a successful authentication. This is a simple POC that implements authentication bypass. Okay. After analyzing the authentication bypass vulnerability, let's shift our focus to another important part of aicloud, the SMB DAV modules. The modules define several custom, no-standard HTTP merged that greatly expand the attack surfaces. There is a critical path rule in the lighttpd configuration. So what does the configuration actually mean? This setting allows whether the user's path does not match the specific pattern. The root path will enter the relevant configuration block through its methods. This exactly the exact path was decided early to bypass authentication. The query configuration block executes the SMB modules, letting it use all its features, including custom HTTP masters. We analyze the SMB modules. We discovered a critical command injection vulnerability in this master. The server processes the char memo from users and extract key fields, including private key, cert, intermediate cert. The values extracted from the char memo and have not been properly validated and directly passed to the system function for execution. This implementation allows the attacker to inject malicious commands by carefully crafting the cert content. We discovered another critical command injection vulnerability in the apply app merged. This vulnerability is more stable than process vulnerability. Involve vulnerable misuse and incomplete input checks. The apply app must process two critical HTTP handlers, set MV1, which set routers configurations, RC service, which runs service control commands. This code tries to check two values for security, but there is a fatal error. It checks the set MV1 variable when it should be checking RC servers. This misuse of variable causes RC servers values to bypass some of the security checks. And the function checks whether a variable is valid, but its checks are not zero. There is also a replace special chars function that tries to clean out dangerous characters, but is not perfect either. As can be seen later, the process RC server value is directly passed to the system function for execution. The code was wrongly designed to use these two functions together to ensure that the RC server value from users is safe, but its case has variable misuse. The check is for status stable, which allows a command injection by using backward. It was supposed to direct the value of RC service. Now, let's analyze the vendor's fix for these vulnerabilities. Instance all of this request goes wrong. It directly returns to a 401 unauthorized error when handling the host query command. The use is a validate string function for vectors. Although the function is not perfect, the double quotation mark package that does affected prevent command instruction. Next, let's analyze another vulnerability fix taken by a vendor. By checking the attacked service, the vendor have moved a lot of dangerous custom HTTP models to prevent new values from popping up. Well, my friend Spin will show the remaining part.
Now, let's take a look at the vulnerabilities chain related to a challenge named router 4 from the SIS real-world CTF. This chain includes three key paths: a checker bypass, a cycle inject, and a stack buffer overflow. By using these together, an attacker can first bypass paste checks, then leak informations, and finally run any code they want. In the lighttpd configuration file, the /smb/url paste is set to be handled by webdev module. This means the webdev module will manage both /smb and its subfolders. And the document root set to /user/lighttpd. The webdev module is fully enabled, and the read-only flag is turned off, means both read and write operations are allowed. When the program reaches the webdev module, the moved webdev sub-request handle function performs a check and blocks certain requests. If someone tries to access /smb/ with a mouse that is not get, it will be returned a 403 forbidden. But here is an issue. The code uses strncmp for the compilation, and when the paste is not when the paste is /smb without the trailing slash, which match the router defined in the lighttpd configuration, the check doesn't work. So, attacker can take advantage of that and bypass the URL check. In the webdev module, the moved webdev sub-request handle function handles server HTTP methods. One of these methods is the profile media list. There is a cycle inject vulnerability in the profile media list method. The value of the keyword variable is taken declared from the request header. Is then added into a cycle query using printf and execute. Allow the code check for single quit in place. It can be easily bypassed. Attacker can bypass the check using simple URL encoding trick. The keyword value is URL decoded before it's used in the cycle query. This means attackers can send encode payloads to bypass input validation, and the payload still works after decoding. But how does the cycle inject lead to memory leak? Asus AI Cloud uses cycle 3 for for its cycle operation. In SQLite 3, there is a special function called fxc233 tokenizer. This function is used to get the pointer to a customer tokenizer module. If the attacker called fxc233 tokenizer with only one argument, the tokenizer name, it will return a pointer to a SQLite 3 tokenizer module struct. This gives us a memory leak. We can leak memory address from the SQLite process. Use select FTS tokenizer parameter simple your only one argument. By using the pointer returns for a simple tokenizer module, an attacker can calculate the base address of a library SQLite 3. This allow we to bypass SLR. This is a big ending. Inside the web dev module, the mood web dev support request handle function also handle HTTP requests like copy. These methods are used to manage file actions like copying or moving files through the web dev service. Also, you can use move. In the copy methods, there is a function called change web dev file path in here. This function deals with the destination header and affects how file paths are processed. Destination keyword and here a buffer of size 4096 is passed as a parameter to the change web dev file path function. Inside, there is a code to replace str, which is where the problem begins. The replace str function doesn't check the length of the data, and it uses explanatory to write into a fixed size buffer. This can cause a stack buffer overflow, which is a serious security bug. Through this stack overflow vulnerabilities, we can easily control the program's return address. And with that, we have successfully trained all these vulnerabilities together to Arch code execute. And now is a demo time. We use Cume to run HTTPD and map the port from 443 to the local 8443. And when we successfully exploit it, we will create a hack file on the temp/temp. and try to leak information, leak memory, and we tried because they have some better chart. Final successful. Okay. Next, let's take a look at a page for these vulnerabilities. After the page, the replace str function now has parameter mask size to limit the length of the input. Additionally, the check for the request path was changed from /SMB/ to /SMB to fix the URI check bypass. After the page, the URL is decoded before checking to prevent SQL inject attacks. Okay, today we will walk you through some interesting vulnerabilities in the AI Cloud module. Let's break them down. First, the AI Cloud module says user agent is Microsoft Web Dev. I think you already authorized. And some HTTP must take user input and pass it to the system. Imagine this. You give me a string. Cool, let me just call system function. That's for you. It's a classical case of a commander inject. Next, we come to a neat trick with SQLite. The FTS3 tokenizer function leaks memory pointers. By calculating the base address, attackers can bypass SLR. Finally, we have a class vulnerability, stack overflow, using expletive function with an unchecked buffer. That's all for today's presentation. Thank you, everyone.
So thank you very much for the talk. If anyone has any questions, please look for them after the talk, or they'll just be around outside. Okay?